Hello, I'm Dr. Chris Jorgensen from Sul Ross State University. The title of my talk today is Using Apolar Invariants to Find Roots of Polynomials. So, throughout this talk, we'll let P of x be a cubic polynomial in one variable and Q of x a quadratic second degree polynomial in one variable. And now notice the binomial coefficients we'll use. And a sub I and b sub j, the coefficients of the polynomials are complex numbers. In Rhoda from 1998, it's shown that the coefficients, if the coefficients of p and q satisfy the polynomial equation, this polynomial equation, which is called the A23 apolar invariant. And I won't be showing why these invariants are invariants. It takes a little bit too much time, but it's in the detail of that is in Jorgenson 2013. And if you go to the Sul Ross website and look up my name, Chris Jorgensen, under the directory and look in my CV, you'll find links to my papers on this. Now, if this equation is satisfied, then P and Q are said to be apolar or A23 apolar, and this provides a method for finding the roots of the cubic P of x. So given a general cubic P, one may solve for a quadratic Q that's apolar to P. In the case where the quadratic has two distinct roots, R1 and R2, it's shown in Jorgenson 2013 that the cubic may be rewritten in this form, and then it can be solved using this form. So this method is also discussed in Kung Rhoda from 1984. You can find online. Let's look at this example. We have a cubic equation, polynomial P, and if we identify the coefficients, a sub 0 is the leading coefficient, and that's 30 in this case. A sub 1, the second degree coefficient, is 0. A sub 2, since we're using the binomial coefficients, a sub 2 will be 100 over 3, and then the constant a sub 3 is -9. And then what we'll do now, we'll solve for a quadratic that's apolar to the cubic. And so we'll take this equation we're trying to solve, and we'll solve it by using a system of equations here, of two equations, and we'll use that to find the b sub i's that are the coefficients of the quadratic. And so we can solve the system by using a augmented matrix here. And notice the first column aligns with b sub 2, and second column b sub 1, and the third column b sub 0. So if we plug in the values we have for the cubic to define the cubic in our example, that will give us this augmented matrix that we can row reduce, and then we can solve for the b sub 2 and b sub 1 in terms of b sub 0, which serves as a free variable. And so the space of quadratics actually is a space because it arises as a null space of a 2×3 matrix. And so this is a generating polynomial for the space of quadratics that are apolar to P. And so we can call that space S sub P, and by making a linear change of variables, we let b sub 0 equal 900t, then that will allow us to write our generating polynomial with integer coefficients, and that's a one-dimensional subspace isomorphic to a vector space subspace of C3. Okay, so, and I just said that, so we'll skip over that. And now if we solve this equation, we get two distinct roots in this example, R1 and R2. And now, by using other reasoning involving linear algebra and vector spaces, which I won't take the time to go into in our limited time, we can write P of x as in terms of the roots of the quadratic and the coefficients of P. And then that'll allow us to solve for the roots of P. This gives you a little bit of idea of what's involved here. We can gather the x expressions over here. And then if we let y be the x expressions and d be this, d in this case is non-zero, so we'll get three complex roots for y. And then when we convert back to x, that'll happen. This is a one-to-one function, so we'll get three distinct roots for x also. And so when you use this method for our P of x here, we actually get three roots, A, B, and C. And B is a real root. And, you know, if you have a cubic polynomial in one variable, it'll always have at least one real root. And in this case, the other two roots are non-real complex and they're conjugates. The conjugate pair theorem, they would be conjugates. Now, Rhoda says this method of solving a cubic equation is the only one I can remember. And all right, so here's some theorems. Now, theorem 1 says if Q is quadratic and P is cubic, as we saw in the example, then if Q has a multiplicity 2 root at R, then P, which is apolar to Q, will have a multiplicity, will have a root at R of multiplicity at least 2. So this is a different scenario where there are repeated roots. In this case, they actually, Q and P will actually share roots. Now, if P has a multiplicity 2 root at R, then any apolar quadratic Q of X will have a multiplicity 2 root at R also. Now, if P has a multiplicity 3 root at R, then Q, apolar quadratic, will have a root at R, and then you can find one that's apolar that's multiplicity 2, is what that theorem says overall. That leads to a corollary, and if P is a cubic and Q is a quadratic and they're apolar, and Q has 2 distinct roots, this is quite the example, then either P has 3 distinct roots, all different from those of Q. That was like the example we saw. Or P has 1 triple root that Q and P share. Okay, so now we want to try to extend these methods to cubics, to quintics and cubics. So if we have a quintic polynomial, we'll use similar notation. So we'll use binomial coefficients, and the coefficients of S d sub I can be complex. And there's our cubic again. Now there's an A35 apolar invariant, and if they satisfy and equal 0, then they're said to be A35 apolar. So if we're given a quintic polynomial, let's say, we have the values for the d sub i's that we can plug into a system of 3 equations and 4 unknowns, because the unknowns will be for the cubic. And we solve that system of equations using an augmented matrix. And we'll get back to that with our example. Now let's corollary. If a quintic polynomial S is apolar to a cubic polynomial, then S cannot be of these 2 forms. So these are forms where we have 3 consecutive powers of X with 0 coefficients that can't be, so these quintics can't be solved using apolar methods. Now let's look at a lemma though. If S is apolar to a cubic, then S will have a root of multiplicity 3 at T if and only if the cubic also has a root at T of multiplicity 3. And then that can be used to solve the theorem. If P and Q are, not P and Q, if P is a cubic and S is a quintic and they're apolar, and P has 3 distinct roots, A, B, and C, then S can be rewritten in this form. So this is similar to the case for quadratic and cubics. And the k sub i's here, the coefficients, can be solved for in terms of the roots of the cubic and the coefficients of the quintic. So here's an example here. It's a nice, simple-looking quintic polynomial, but we can show that using the rational root test that this S does not have any rational roots. Now, if we go back to the general form to identify the d sub i's, we know that we get these values for D1, D3, and D5, and then 3 of the coefficients are 0. Okay, and now if we go back to our augmented matrix and substitute these values in for d sub I, then we can solve for the cubic equation, row reduce this augmented matrix, and then we'll be able to solve for a sub 3, a sub 2, and a sub 1, all in terms of a sub 0. And so the leading coefficient of the cubic will act as a free variable. And so we'll get a space of cubic polynomials that are apolar to the given quintic, and is similar to the previous case for cubics and quadratics. So the space of cubics arise as being a null space from a 3x4 matrix. So it is a vector space, and we can make a change of variables so that our generating polynomial has integer coefficients for the cubic set of cubics. But notice this is one that we have already found the roots for. That was A, B, and C we found earlier. So we can go back and substitute those in, and then use the values we have from the theorem for the k sub i's, and here what they are in the general form. And in this example, we get the k sub i's in terms of the roots of the cubic, A, B, and C. And so we can write that out and write out our quintic there. Okay, So now here's some questions in future work. Now, with reference to this last example, can the roots of a quintic polynomial given from theorem 3 and the last example, where all three k-subis are non-zero, can that be solved for algebraically? Is there some method of exact mathematics that might be harnessed to find these roots? Now, how do apolar polynomial methods align with Galois theory? Can the specific forms given for the k-subis in theorem 3 be used to shed light on the quintic polynomial equations in one variable that may be solved for by radicals? And can a new criteria for solvability by radicals be offered in the language of apolar polynomials? So question 4 says, what more can be learned regarding the roots of a quintic S in the situation in which a cubic P has is apolar to the given S, has a root of multiplicity 2, which is also a multiplicity 2 root of the quadratic Q of X. Now, in this case, the examples I've seen, the roots of the Q and the P that they share don't shed light on the roots of the quintic, because the roots are only multiplicity 2. And what methods might be brought to bear on those other quintics that are not apolar to any cubic polynomials? So some outstanding questions still to look at. So here's a paper for mine 2019 and 2013, and the Kung-Rota paper, and the unpublished one that was from Rota's speech at the joint conference in 1998 in January, the AMS and MAA. And here's another paper by Baishish on the on apolar polynomials. All right, so that's all.